I'm sure you've heard of Retatrutide, which is not FDA approved yet, but it's GLP and GIP and glucagon receptor agonist. So this video is going to be about what are those things. GLP-1, GIP, and glucagon are three hormones that have become central to modern metabolic medicine as far as the craze around Retatrutide and what it's shown in the research studies so far. So I'm sure you've heard of GLP-1 medications and probably GIP, because GLP-1 plus GIP receptor agonist, that's Tirzepatide, which is Zepbound or Mounjaro. So it can be confusing because GLP-1 and GIP generally help the body respond to a meal and increase insulin secretion. Glucagon does almost the opposite. It tells the liver to make or release glucose. So why would we want to activate all three? So in this video, we're going to look at what GLP-1, GIP, and glucagon actually do, where they're normally produced, how they affect the pancreas, liver, GI tract, brain, and fat tissue, and why scientists are now combining the pathways for this new Retatrutide treatment, because there are other medicines using various combinations of this. So three distinct signals and one interconnected metabolic system. Let's start with the simple framework. What happens after we eat versus what happens when we're fasting and we haven't eaten? So normally after a meal, nutrients enter the GI tract, glucose rises, the body needs to appropriately increase insulin secretion so glucose can be taken up and stored or used by tissues. So two important gut hormones help coordinate that response, and that's GLP-1 and GIP. Those are the only two incretins we have, and some people say incretins, because they enhance glucose-stimulated insulin secretion after nutrients are ingested. So they're different hormones. So during fasting, the metabolic problem is different. The body still needs a continuous supply of glucose, particularly for tissues that heavily depend on glucose. And so the liver, therefore, releases glucose into circulation. And one of the major hormones responsible for that is glucagon, primarily produced by pancreatic alpha cells. Beta cells produce insulin. So these hormones aren't good or bad. GLP-1 isn't always suppressing glucagon. GIP doesn't always increase glucagon. Glucagon isn't simply a harmful hormone that raises blood sugars. Their effect depends on glucose concentration, nutritional state, receptor activation. So that's kind of an important concept to keep in mind throughout this video. So in the fed state, food goes to the intestine, activates GLP-1 plus GIP, which affect the pancreas, causing increased insulin. That's one effect. In the fasted state, lower glucose goes to the pancreas, which releases glucagon, which goes to the liver, which causes glucose production from the liver or release. So let's start with the incretin GLP-1. GLP-1 stands for glucagon-like peptide 1. And despite the name, though, GLP-1 is not glucagon. GLP-1 is produced from the pro-glucagon molecule. That's primarily the enteroendocrine L cells in the intestine. They respond to nutrients being present. So GLP-1 has multiple effects, enhances glucose-dependent insulin secretion from the pancreas. That word glucose-dependent is important. GLP-1 receptor activation increases insulin secretion much more strongly when glucose is elevated than when glucose is normal. This is one reason why GLP-1 receptor agonists have a very low risk of hypoglycemia if you're not using it with insulin or other secretagogues. Second, GLP-1 suppresses glucagon secretion when glucose is elevated. That can reduce inappropriate hepatic liver glucose production. Third, GLP-1 decreases gastric emptying, right? That slows the delivery of nutrients into the small intestine, so you don't have that high postprandial glucose spike. Fourth, GLP-1 activates neural circuits, which see my other video about that, which are in the gut, like the vagus, and then also maybe in the organs around the brain. So the weight loss produced by GLP-1 receptor agonists is not because they speed up metabolism. The major component is because people eat less because hunger and food intake are reduced. But native GLP-1, our own GLP-1, extremely short half-life, minutes, so it's gone quickly by the DPP4 enzyme. That's why medicines were developed that produce much longer activation at the GLP-1 receptor. So GLP-1 increases glucose-dependent insulin secretion, decreases glucagon when glucose is elevated, decreases gastric emptying, decreases food intake, increases satiety. The effects differ between physiologic GLP-1 and pharmacological receptor activation. So that's kind of the GLP-1s, right? The next is GIP, the other major incretin. So GIP stands for glucose-dependent insulinotropic polypeptide. It was originally called gastric inhibitory polypeptide, but that doesn't describe its major physiological role. GIP is produced by the K cells in the proximal small intestine and is released rapidly after nutrient ingestion. And like GLP-1, GIP is also an incretin. Its most established action is to enhance glucose-dependent insulin secretion from pancreatic beta cells. In fact, GIP is an important contributor to what's called the incretin effect, which is the observation that oral glucose produces a greater insulin response than IV glucose producing a similar glucose concentration. That's because it's of the gut effect. So GIP is different though from GLP-1. GIP doesn't have the same robust effect on gastric emptying as GLP-1, and its effects on appetite are much more complicated than simply saying GIP is an appetite suppressant. GIP receptors are found in multiple tissues involved in metabolism, including the islet cells and adipose tissue. It can affect glucagon secretion. At lower glucose concentrations, GIP can stimulate glucagon secretion, potentially helping defend against low blood sugars. At higher glucose concentration, its insulinotropic effect, how it helps us release insulin, predominates. That means GIP can participate in maintaining glucose homeostasis both ways. But this physiology can be altered in type 2 diabetes, where it doesn't work right in patients with type 2 diabetes. And this is one reason GIP biology is much more interesting and complicated than simply the description of it's another incretin. So GIP, it increases glucose-dependent insulin secretion, important component of the incretin effect. It can stimulate glucagon, particularly at lower glucose levels. It has effect on adipose tissue and other metabolic tissues, and it's complex in type 2 diabetes, doesn't work as well. So now let's talk about glucagon, the fasting hormone. Glucagon is produced primarily by alpha cells in the pancreatic islets. Its classic role is to defend against falling blood sugars. When glucose levels fall, glucagon acts primarily on the liver. It stimulates glycogenolysis, which is the breakdown of stored glycogen. And it stimulates gluconeogenesis, the production of new glucose from substrates including lactate, glycerol, and amino acids. The result is increased hepatic glucose output. This is a very essential physiology because without an appropriate glucagon response, the body has a much harder time defending against low blood sugars and maintaining glucose during fasting, which is often overnight when we sleep. But glucagon does more than regulate glucose. Glucagon receptors in the liver influence lipid metabolism and amino acid metabolism, and glucagon signaling can increase energy expenditure and promote fat oxidation in certain experimental and pharmacological settings. So this is where things get really interesting for obesity treatment. If you activate the glucagon receptor by itself, you raise blood sugar. So why would you ever want to activate it therapeutically as a medication? Because researchers are interested in combining the metabolic effects of glucagon with hormones such as GLP-1 that counterbalance the glucose raising effects. In other words, glucagon has potentially useful metabolic effects, but its glucose raising effect is the problem that has to be solved. That's one of the biggest fundamental ideas behind the multi-agonist GGG. So let's put these hormones next to each other. GLP-1 and GIP are incretin hormones. Both are released after nutrient ingestion and can enhance glucose-dependent insulin secretion. But they're not identical. GLP-1 has a particularly important role in reducing gastric emptying, food intake, when its receptor is pharmacologically activated. GIP has a different physiological profile, including important actions on pancreatic beta cells and potentially alpha cells and adipose tissue. And there's also a whole complicated thing about, do we inhibit GIP or do we stimulate it? Because remember, Amgen has the product Meritide that actually is a GLP-1 plus an inhibitor of GIP, which appears to have the same beneficial effect as the stimulator of GIP. So some people think GIP in this Tirzepatide actually inhibits, it's overstimulating the receptor, so it actually inhibits the release, inhibits the receptor of GIP. And what's really crazy is we really don't know. Here we have Tirzepatide and how it works so well. It's stimulating the GIP, and here we have Meritide also works so well. It's inhibiting the GIP. So which one is it? There's some animal studies that suggest that inhibiting it is actually what we're doing with Tirzepatide. And finally, there's glucagon. Glucagon is primarily a counter-regulatory hormone that increases hepatic glucose production, particularly during fasting and if you're starting to have low blood sugars. But these pathways all interact, and that's critical. Here's a table of GLP-1, GIP, glucagon, the primary source where they are produced, the major stimulus, their effect on insulin, their effect on gastric emptying. In clinical trials, Tirzepatide produces substantial reduction in both blood glucose, body weight, but an important scientific point is that we still don't have every aspect of GIP's contribution completely worked out. So it's tempting to say GLP-1 does this, GIP does that, together you get this result. But what I'm telling you when I'm talking about Amgen's product that inhibits GIP is human physiology is much more complicated. The effect of a receptor depends on where that receptor is expressed, how strongly it's activated, what other receptors are being activated simultaneously, and the metabolic state of the person receiving the drug. That's why multi-agonist pharmacology is not just about turning on more receptors. It's about finding the appropriate balance of the receptor activity. That is especially important with glucagon since that can raise blood sugar. So GLP-1 can reduce food intake, improve glucose regulation. GIP can complementarily improve glucose and metabolic signaling. Glucagon can increase hepatic energy expenditure and influence lipid and amino acid metabolism, but it also increases glucose production. So the goal of a triple agonist isn't necessarily to maximally activate every receptor, it's to find this balance that is beneficial to the body. So there's several important takeaways if you're taking or considering a medication that targets these pathways. And a lot of people taking Retatrutide on the gray market, but there's a lot of people wanting to start it in 2027. We think it will probably be approved. First, GLP-1 receptor agonists and dual or triple agonists, they're not interchangeable. They have different pharmacology, dosing, indications, efficacy. Second, GI adverse effects are common with incretin-based therapies, especially at the beginning and when you escalate the dose. Third, GLP-1 and GIP stimulate insulin secretion in a glucose-dependent manner. That helps explain why these medicines have a really low risk of low blood sugars, but that risk isn't zero, particularly when you combine them with insulin or other secretagogues like sulfonylurea. And finally, we need to distinguish physiology from pharmacology. The amount of naturally circulating hormone in your blood after a meal is not equivalent to what happens when a medication produces a sustained pharmacologic receptor activation. And in the case of GIP, maybe, like Tirzepatide, maybe it's actually regulating that GIP receptor. So, in inhibiting it. The distinction is very important when interpreting studies of these drugs. Putting everything together, GLP-1 is an incretin hormone that helps coordinate the response to food. It enhances glucose-dependent secretion, suppresses glucagon, and when glucose is elevated, slows gastric emptying. When its receptor is pharmacologically activated, reduces appetite and food noise. GIP is the other incretin hormone. It's a powerful glucose-dependent insulin secretagogue, has additional effects on pancreatic alpha cells and other metabolic tissue. Its effect on glucagon are glucose-dependent and can differ in type 2 diabetes. Glucagon is a major counter-regulatory hormone. It helps maintain glucose during fasting and low blood sugars by increasing hepatic glucose production while also influencing lipid and amino acid metabolism and energy expenditure. So these hormones aren't competing. They are part of the same metabolic system. The future of metabolic medicine may involve deliberately combining these signals. There's different combination of these in research now to coordinate a metabolic response instead of targeting any single pathway. So GLP-1, GIP, glucagon, 3 different receptors, 3 different biological signals, potentially when carefully balanced, like in Retatrutide, a very powerful approach to treating metabolic disease. I'm Dr. Susan Bryan, board certified endocrinologist. I also do clinical research with various GLP-1 medications and Retatrutide and Tirzepatide. But these are not paid ads. I don't receive any money for these. This is only for educational purposes. Leave me any questions below. I hope this cleared up a few things for you. Bye.